Log on, tune in, find out. Another good idea from Cambridge.
Michael Green and Stephen Miller on automorphic forms. And we already had a talk from Stephen Miller on more technical aspects in mathematics, and this, I guess, will be about string theory aspects.
Yes. Thank you. So in that talk, I will try to present the main result and as well motivation of the recent work we did with Michael Green and Stephen Miller on automorphic, on determining some properties of string theory interactions, and in particular the properties of this interaction under the duality symmetry groups and supersymmetry. So one way to encode the effect of string theory when one computes a physical process is to look at the low energy effective action that string theory gives you. So the low energy effective action of string theory in d dimension starts, as we know, by the Einstein-Hilbert term that tells you about gravity in d dimension. And here I will write things in the Einstein frame. So this is the Planck length in d dimension, and this is the dimension. This is dimension 2 operator. And string theory gives you correction to general relativity and supergravity in d dimension by higher derivative operator. So the operator I will be looking at are the ones that are given by 4 powers of the Riemann tensor. So they are contracted in a specific way, and the string theorists in that room know that which way I'm contracting this Riemann tensor using the famous T8 operator. The point is that since I will be only looking at n equal 8, the maximal supersymmetric case, which is the toroidal compactification of string theory, supersymmetry restricts me to a single Lorentz scalar for the r to the 4th term that is going to factorize everything. So I know that there's a unique structure, and here there's a coefficient that I denote E00 and as a superscript has to do with the dimension, and here the argument are scalars that parameterizes the vacuum where I am sitting, okay? And so I will be looking at this term, and I will be looking at the next term in the derivative expansion, that is 4 derivative on that term, 1, 0, phi, d dimension. And then I will be mentioning this one, although I won't say much about it in that lecture due to the 6th or to the 4th term. Okay. So phi are the scalar field that parameterizes the vacuum of my theory in d dimension, and phi lives in a coset space, which is given by phi parameterizes a coset space that I'm denoting by ed plus 1 divided by kd plus 1, where ed plus 1 is the continuous duality group in d dimension, where okay, I think if I write this is correct. This is if I want d plus 1, if I want 7 here, I suppose, okay, I don't remember what this is. Okay, yes, in 4 dimension it should be, that gives me, no, that's not, okay, yes, this is correct. So if I, so that means in d equal 4 dimension, the duality group is E7, which actually is the real split form for E7 that we know is the continuous part. The maximal compact group is SU8 divided by Z2, and this has to do with the continuous part. So my phi lives in this coset space, and the important point about string theory is that, if that was the whole story, life would be boring, because I would not have much, invariant function, non-trivial invariant function on that transformation of E7, but string theory tells us that actually we have to restrict ourselves to a discrete subgroup of this duality group, E7. So E77Z is, you can think it about two ways. Either you can think it about E77R intersecting SP56Z. So this is the usual flux quantization that you have in equalate supergravity, and 56 being a faithful representation of E7. It's a very valid definition, and that turns to be the same as the Chevalier definition of the discrete subgroup. Okay. So, I will mention in a minute what are the group in higher dimension, but let me start already from here. So, since I'm computing something which is part of the effective action in string theory, all my effective action here has to respect the symmetries of string theory. So in particular, it has to be invariant under the action of the discrete subgroup E77. So that means all my EPQ, in that case D equals 4, have the property that they have to be automorphic function under the action of gamma in E77Z. Okay, so this is what I mean by automorphic, and this is, so all these guys are to be automorphic functions. Yeah, and so you will see in a minute that for the first cases here, this is essentially residues of Eisenstein series, very special residues, and that case is not an Eisenstein series, and you will see why. But I will be, the detailed structure of this coupling in various dimensions is not so well known, so I will not spend too much time on it. Okay, so now I need to put more constraints if I want to determine what are these functions. So we know that there is one very important symmetry of string theory, which is supersymmetry. And okay, supersymmetry is very difficult actually to quantize. To explain. How supersymmetry acts, because if I try to write the action of supersymmetry in component action, and I try to, for example, do the supersymmetric variation of that action and determine, the constraint on this coupling from the action of supersymmetry. People would try that in that room. Know that it's an horrendous task. Okay. On the other side, we know that supersymmetry is making these couplings very special. Okay. So we say that this one, for example, is protected by supersymmetry, is what we call 1/2 BPS coupling. This one is again protected 1/4 BPS, and this one would be 1/8 BPS. But clearly, what does it mean? In a sense, you can ask yourself, where do I see that R to the 4th is half BPS? Okay. So if I compute an amplitude, I would say zero mode saturation, or if I have a superspace construction, I would say it's represented by half, maybe superspace integral or whatever it is. But this is not a very completely satisfactory understanding, and as well, because supersymmetry is only an on-shell symmetry. It's there's still some question about exactly what we mean by that. So I will not try actually to derive really where the equation comes from, but one consequence of supersymmetry, which will be actually enough, is that all these objects, they satisfy some Laplace equation And so I have here my moduli, they are in this coset space, so I can define the Laplacian that is associated with that coset. It's a very well-defined differential operator. So then, okay, when I write nabla d, I refer to the Laplacian on the coset space. Yeah. So if I have d plus 1 here, d plus d equals 10. Okay. And we found with Michael and Steve that the E00 coupling satisfies the differential equation that I'm writing to you. D minus 2, 6 pi 8. Okay, so let me pause a little bit and make some comment on this equation.
Yeah,
Yes.
can you just outline a little bit how supersymmetry gives you a Laplace equation?
Okay, so, well,
I normally think of supersymmetry as being some sort of first order equation,
Yes.
killing spinners. So.
well, the way it worked, okay, so, yeah, okay, let me tell, okay, so in 10 dimension, you do, when you act with supersymmetry, what happens is that you are going to look at the variation of that action. So you will relate different coupling in that action. Okay, so let me do in 10 dimensions, type 2B. You will have the object that I call E00 to the 4th, but as well, one of its supersymmetric completion will be the Dilotino to the lambda to the 16. And this guy actually, so in that case, the duality group is SL2, so there is SL2 over U1, it carries a U1 charge. So here you are going to have a form that will have some weight. Okay, I mean, actually the notation has to be, so it's 10, and the weight, for example, is 12, whatever, I mean, some notation. So what's going to happen is that when you do the supersymmetry variation, you will vary that term, and that term as well, but you will relate as well to a guy that is at this level, which, I mean, I think some coupling to the action. So you will have a first order differential equation that will couple this coupling to the coupling here. So you will have a system of first order first order differential equation, but they are coupled.
Oh, I see.
So then when you try to solve that system, you will end up with second order differential equation on each of the coupling. So, I mean, I cannot really explain that because, I mean, it's highly technical, and I don't think this is very illuminating because I don't think that really shows, I mean, it's instructive, but I don't think that explains what we want to say about, the action of supersymmetry. I mean, it's a consequence of it. Okay. So here, I'm writing equations that, okay, so the way that I've given to you without justification, but let me comment on that. So you see, there is, here this is a delta function. That means this is 0 only when d equals 8, but when the dimension is not 8, this is really 0, okay? So first think about when d is not 8. So I'm getting that this object has to be an eigenvalue of the Laplacian, okay? So, although, I mean, if you think about the SL2 case, I mean, if you have the differential equation plus the boundary conditions at the cusp, then you can solve that equation. So in 10 dimension, if I have a differential equation like that, I know this is the SL2 Laplacian, for the case I mentioned, with the boundary condition telling me that this has a polynomial graph at the cusp, I know this is going to be an Eisenstein series. Okay, so there is a special case where in d equals 8, actually the series that we'll have to consider as a pole, because you see the eigenvalue is vanishing. So if we don't want that the solution is just a constant, I mean we know that we should sit on a pole. Like it's like the SL2 case, you know, when you are S equal 1, and this comes from taking care of the pole. I will mention that later in the talk. So this series as well, I mean, except in 7 dimensions, it's an eigenvalue of the Laplacian, and in 10 dimensions, with the boundary condition, it's an Eisenstein series. And here you see that at this level, something very interesting happens. Is that, okay, forget the delta function part that comes in only in 6 dimensions, but for example, in 10 dimensions and over dimensions, it's not an eigenvalue of the Laplacian. Here there is something that is the square of this guy. And so you already see that even if the very few cases here could certainly be simple object, this is certainly not a simple object. So already for the SL2 case, I would have an equation that is actually for SL2 case, let me write it, SL2 over SO2. So the first equation is, so I'm using the usual physics convention, which is the opposite sign to, you know, mathematicians. So tau is in the upper half plane, and so minus 3/4. So E00 10 equals 0, 5/4 E10 10 equals 0, and Napler minus 12 E10 01 is minus E10 00 square. Okay. So here what you have, okay, I mean I will explain that this is a free half Eisenstein series, so this guy is not annihilated by the Laplacian, so I can try to solve that equation. So this equation has a solution. In 10 dimensions you can show that this equation has a solution. It's not an Eisenstein series, so it really goes beyond, I mean, the naive case that you have already here. So, and that shows actually that if you want to understand, you know, how supersymmetry restricts the effective action of string theory in every dimension, I mean, then to higher order in derivatives is going to be a big mess. I mean, in sense, I mean, you expect that the structure of the source term is going to be generic. It's maybe, I mean, lower order terms is going to source, I mean, higher order interaction, which is kind of obvious from an unfair approach, I mean, on-shell deformation of the supersymmetry algebra. Though, by looking at this equation, it's very difficult to, I mean, to grasp really what supersymmetry does for you.
So in general, this Laplacian acts on what space? Is the Laplacian on what space?
It's on the scalars that are in the coset space of the.
So in 10 dimensions, only the.
Yes, it's only the SL2 part. I mean,
otherwise, there is.
I mean, in 4 dimensions, this is E77 divided by SU8, so this is the coset space. So here I can say something, I mean, as well interesting, is that, okay, so string theory, superstring theory is defined in 10 dimensions, so naturally, I mean, my dimension D is smaller than 10, and D and the rank of the group satisfy the simple rule, but then you see something interesting is that, okay, so when D equal 2, my eigenvalue blows up, okay? So I slightly anticipated from what I'm going to say, but telling that this is going to be an Eisenstein series. So the Eisenstein series, you know, they satisfy the eigenvalue of the Laplacian and the eigenfunction of the Laplacian. The eigenvalue is the Casimir, quadratic Casimir. When D equal 2, by my rule, actually, well, anyway, for D equal 2, my duality group is E9, and it's, you know, then the Casimir just, I mean, blows up because it becomes infinite. You have to regularize. I mean, Katz explained how to do it. So there is something that goes together with the mathematics and the physics that, you know, the blow up of the eigenvalue is nice in a term of, you expect that something happens for E9. So there is a way to regularize, I mean, to make, actually Garland constructed Eisenstein series for E9, but, okay, it's not clear whether or not this is relevant to the physics we want, so I won't say anything. one,
Yeah, sorry. I mean, actually, though, if D is 1 or 0,
yes.
then
So for D
there's
equal
no
1, you go to
singularity.
E10. For D equal 1, you go to E10 if you know what E10 is. So, I mean, this apparently makes sense. I mean,
Yeah.
according some discussion with Axel Kleinschmidt looked at this equation in D equal 1 and somewhat, I mean, found that they can make sense and it can, I mean, actually that can match what you expect from E10. Although I have no idea about what is E10Z, I don't know what are automorphic form for E10Z. But anyway, so I will be restricting myself to up to 3 dimensions. So that means group going from E8 till SL2Z. Okay. So now, one thing that, okay, so know that I have a differential equation. If I want to tell you what are these functions, I mean, I have to tell you what are the boundary conditions. Okay. So, yes, I think I will do it this way. And I think the best way is to draw. So the lowest dimension I have is 3. And then in that case, the duality group is E8. Okay? Okay. So when I have E8, I can look at 3 different maximal parabolic subgroups. So I'm interested in maximal parabolic subgroups that I obtain by deleting, so by removing the first node of the linking diagram of E8, okay, then I will see here SO 7-7 symmetry, okay? So that means if I remove, so the maximal parabolic subgroup associated to the first node of the linking diagram, so that I know P alpha 1, he has a Levy factor, there's a unipotent factor, and the Levy factor E alpha 1 will be of the form GL1 times SO. Okay, now I'm writing SODD because for all the E groups that will be SODD. So this is SO77 for E8, and GL1 is the GL1 parameter that tells me how I'm approaching the cusp, is the string coupling constant. Now, if I look at if I look at the parabolic, the maximal parabolic associated with node 2, I will have here the maximal parabolic will be L2 U2, and it will be GL1 times SLD plus 1. So I'm seeing a SLD group that naturally comes from the reduction of film theory on the torus. Okay, so this one will be associated with what I call the string perturbation. This one will be the strong coupling M theory limit, and one important one is okay, well maybe white is when I remove the last node for E8, so which I denote D alpha D plus 1 is P alpha D plus 1 is L alpha D plus 1. So I see that for E8 I have E7 that is embedded into the Levy component that I obtain. So the Levy component is GL1 times ED. If I take, so if I start from E8, I can embed E7 in the Levy component associated of the maximal parabolic subgroup I obtain by deleting that node. If I am in E7, I can obtain E6 by deleting the last node, okay? And then I have a succession of groups, so that means I'm starting after E8. Okay, let me draw it. 2, 3, 4, 5, 6, 7, 8. So this is E8. So then I get E7. Then I get E6. Then I get E5. But E5 is SO55. Then I get E4. That is SL5. And now things get a little funny because now if I remove that node, I get what I call E3, that is SL3 cross SL2, still a maximal parabolic. Then I remove one node, but then it's not a maximal parabolic subgroup anymore because I want to have that E2 is SL2 times R plus, which is the duality group in 9 dimensions. So this one is not a maximal parabolic subgroup. So somewhat, it's a bit difficult to draw. And then E1 is essentially one node, it's just SL2. So what I've told you is that the 10-dimensional case is, okay, if you see it from string theory, is the highest dimension. You start in 10 dimension, you compactify, you go E8. If you start from the E8 perspective, and then you have from E8, and then you take maximal parabolics, and then you go back to 10 dimensions. So it's the opposite way of compactification. So why I'm stating that? I'm stating that because so in each, for example, let me take this case here. So when I see that E7 is embedded into E8, so what I can do, I can look at the Fourier expansion of my automorphic form respect to the compactification limit. So the unipotent radical that is here contains the phases that encodes the charge of the BPS states that will be running along my circle of compactification when I go from 4 dimension to 3 dimension. Okay. In that case, when I took this maximal parabolic with node 1, this is string perturbation, and the unipotent factor will contain the phases that encodes the way I'm wrapping the D-brane on the cycle of my torus of compactification and the Neveu-Schwarz fibrane. So in most of the case, for example, at node 1, this factor is abelian, except when you have the Neveu-Schwarz fibrane that comes into the game. So when you are from E7, when you have a SO66, then you start to see that it's Heisenberg. Yeah, okay. And the place where you get the most non-abelianness of the unipotent factor is when you remove node 2, where it's a big mess. Okay. But anyway, so this is the M3 limit. Okay. So one way, for example, to derive now these equations is that if I know the differential equation in 10 dimensions, by looking at the way the Laplacian behaves when I took, for example, a limit here. So if I call little r the parameter of the GL1, I can connect the Laplacian on, for example, E8 to the Laplacian on E7 plus a differential operator, a second order differential operator that acts only on R. Okay? So that way I have an equation that relates my eigenvalue for E8 to my eigenvalue to E7, and then I can crank it to 10 dimensions. And this is the way we get the formula. Okay? So that means the way we derive this equation that I say came from supersymmetry was to use the information that we got in 10 dimensions, and this is the way we got it. Okay? So I'm not claiming that the derivation of that is, it's not very illuminating the way we got it, so, but it's at least, there are various tests that tells us that actually this has to be the correct eigenvalues. Okay? So we know, for example, that this one vanishes in 8 dimensions because you expect that in 8 dimensions one loop for graviton amplitude has a UV divergence with R to the 4th as a counter term, and this is very nice. Then this vanishes in 7 dimensions because you expect that e to the 4th r to the 4th is the 2 loop UV counter term, so you are happy. Then this one vanishes in 6 dimensions because e to the 6th r to the 4th is expecting to be a free loop UV divergence counter term. So everything fits nicely with the physics interpretation, okay? But still, okay? I mean, I think we need to go a little deeper in our understanding of what supersymmetry does for us. Okay, now I can go here. So now that I have the differential equation, I can look at, so I told you that the boundary condition gives you that all these things that have polynomial growth at the cusp. So I can use the information I have in a given maximal parabolic to constrain actually the growth of the series and look for the what is the solution. So if I take the P alpha 1, which is the string perturbation, so in that case the GL1 factor is the string coupling constant. So in d dimensions, so this is which I denote GD. Okay, well, GD is the string coupling constant. Okay. So I take my object, yeah, for example, E00 of phi. So initially phi lives in a coset space of this guy, but now I'm taking inside this guy a subgroup that will be, so I'm taking this parabolic P alpha 1, so that means I will keep as only an explicit symmetry SODD. And the rest of that symmetry is going to be broken by my maximal parabolic. So in particular, so when I do that decomposition in the U factor, my U factor, I mean an element of my unipotent radical, you can think about a big matrix, which here are some phases theta that are related to the wrap D branes and NS branes when it's possible, because it has to be completely wrapped Euclidean on TD. Okay, so particularly you need a 6 torus to have the 5 brane anyway. Okay, so what I'm going to do now is I'm going to integrate, because I want the constant term first. I'm going to integrate over the phases here. So, and the notation is I call it U. Okay, U of Z, U of R, and I just do it with the flat measure, the R measure. I mean usual. I mean d theta measure on that, and I'm getting now an expression that for the R to the 4th is this. So it depends. It will depend on the GL1 parameter as well. So we get 1 over the string. No. Yes. To the power d minus 8 over d over 2 times a constant over gd square plus here an object that has to be an SODD automorphic form, which I know. So this is a thing I want to determine. I can do string computation 3 level, 1 loop. So I know what is A from a string computation. So it's 2 zeta 3. And here I can do 1 loop computation of 4 graviton scattering, compactify on a torus. And then I'm getting some specific SODD as Einstein series that I'm going to explain in a moment, with here some specialization of the parameters, and that's it. Okay, because it's R to the 4th term, where phi now lives in this. Okay. So I mean, it's going to be important for the Fourier mode later, but the point is that when I take a parabolic subgroup and I look at the constant term of the Fourier mode, they are invariant under the action of the group that is left in the Levy also. So here I'm going to get objects that are invariant under SODD. So I can, by string computation, it's just one loop amplitude that you compute, the lattice, you integrate the lattice. So it's a theta series, I mean, for the given dimension where you are. And there is, here I put the 3 level and 1 loop, and there is some overall power. So as you see, this is what I said. I mean, it's polynomial growth at the cusp. So in that case, R square is 1 over G string, GD. So that means when I go to weak coupling, R goes to infinity. So I'm happy, I go to the cusp at infinity. And actually, if you look at this constraint, the fact that there are only 2 terms, and if you try to match with the differential equation, then you can identify what is E D 0, 0. Okay. So we do the same for the overcoupling. There is 3 level, 1 loop, 2 loop. By the differential equation, this is a boundary condition we can solve, identify what are the functions. Okay. So this is just the logic, and since I'm going to tell you what are these functions, I mean, I just want to emphasize that so far I haven't used so much about the properties. I mean, so I've used 2 things. I mean, I've used the differential equation and I've used what we know from string perturbation. So normally this is everything that one can compute. I mean, it's not, so it's the physical input, okay? So know that I have identified my object, I can ask back the question, is that I expect this guy being special under supersymmetry, half BPS, quarter BPS. Where do I see that, okay? So this is essentially what I'm going to explain in the rest of the talk. So, of course, there is the usual argument saying that based on non-renormalization sign is that normally you would expect, okay. So here I'm a priori having a very, very large group, like E8.
Here, a question. The boundary conditions at the cusp, the perturbation theory result also tells you it's regular in the interior of the solution, or you have to assume regularity in the interior.
What do you mean? You mean for finite values of R?
Can I have singularities? Can I imagine singularities in the interior? Yes, for finite values.
Well, finite values of R, I'm not anymore in the weak. I mean, I'm away from the weak coupling limit if I am at finite values of R, right? So the actual solution, okay. Okay, I mean, I agree. I mean, there is 2 things. As a mathematical statement, I can evaluate the constant term of an automorphic form for any values of R, okay? And it's the physical interpretation as the weak coupling string theory expansion is only for R going to infinity, okay? So, in particular, for that guy that has a source term, I have here powers. I will have things that are powers of G string, but I will have as well terms that are exponential minus 1 over G strings. So indeed, I mean, I see that there are potential exponentially suppressed terms which I don't have here. Okay.
No, my question is more trivial. It's simply a mathematical question. If you look at the differential equation for E00, right? I'm just asking whether the solution is uniquely determined by what you know.
Yes. Yes. Because
but poles or other
no. I'm going to say about that. I mean, we can roll out cusp form. Okay. So when I compute this thing, a priori, I'm expecting that the object as a polynomial in R has as many terms as the order of the Veil group, which is very large. So now the fact that we want something that just has two terms, and actually this statement is completely independent of the dimension. So when you are in SL2, I mean, it's trivial that you have two terms, but when you are in E8, I mean, from millions, I mean, you just have two terms. So that means you are sitting at a very, very special Eisenstein series that where the constant term collapses to just two terms, okay? And the fact that there are two terms here, I mean, is special in determining that. So now the question is that, I mean, is there an ambiguity? I mean, is there, for example, an object that I cannot see in string perturbation, actually, so that would have no constant term, that will vanish at the cusp, so that would be a cusp form. So it's very difficult to talk about cusp form already for SL2, so for higher rank group it's even. But we have an argument saying that actually the eigenvalue that we have with the choice of sign of the Laplacian doesn't allow cusp form. So Steve explained that actually that for SLN, I mean for SL2, SL3, I mean, we know where the cusp form sit in the spectrum of the Laplacian, and then we can, by using some other by long promote that to SLN, and in a sense we used an SLN subpart of E7 or E8 to say that okay, the cusp form are not in the same, they would have an eigenvalue that is not in the same sector as the spectrum that we have here. So we don't have, this is the way we roll out cusp form. So in that case, we claim that the solution, at least for the first two terms, is unique, it's completely well defined, I will write a solution. For the last one, I would have to tell you whether or not the solution exists. So in 10 dimensions, I told you that you can convince yourself that the solution can exist. I mean, you use the resolvent, you inverse the Laplacian minus 12. But for higher rank group, I mean, it's very delicate and, well, I mean, the solution has to exist. But as a mathematical statement, I don't know. Okay. So what are these objects? So the series are the following. I mean, it's very, very funny. So D plus D equal 10. So this is for an automorphic form. For, I have to put plus 1 here. Okay, I'm not going to write the dependence on the moduli. But I need to put the solution is known everywhere. But I mean, in some dimension there are some degenerate cases where the simple formula is not. So this is strictly true for D smaller to 7, and this is D for D equal 5, and I will comment on the and D equal 10. So what do I mean by E? So I mean that E, what I call E alpha S, is the maximal parabolically induced Eisenstein series that is given by exponential 2s alpha h gamma g gamma in p alpha z by E z. Okay, so this is my group there. This is my parabolic subgroup the way I defined it before. What I'm talking is that I'm taking all the elements in that coset. So for SL2Z is the stabilizer of infinity. Okay. And then here, if alpha is a simple root, then I denote alpha, W alpha as the weight vector that is such that, I mean, there is a natural product between, duality between root and weight vector. So this is the guy that is orthogonal to all simple root except alpha. And S is a parameter. Okay. So here I'm taking alpha equal alpha 1, and S 3 alpha 5 alpha. Of course, I mean, what you can do is that it's a special case. It's a special case of the Eisenstein series that have been, analyzed by longs, where the formula is lambda plus rho, h gamma j. Oh, I have to define what is this. So if I take an element in my group, I do the n and k, so it was a Y decomposition, so A is the diagonal part, so I'm taking the diagonal part here. So in a sense, this is what you do for SL2Z. So for SL2Z, what you do is that you have Es of tau is sum gamma infinity SL2 is the imaginary part of the action of gamma on tau to the power S. So essentially what you do is that you take the direction in the Cartan torus, you raise them to some power, S1 to SR, R is the rank of the group, and you just look at the action of your discrete group on it, okay? So of course this is a big object. What is nice is that there are analytic continuation, there are functional equations. So in particular, I can choose over alpha and S that are in the same Veil orbit, but what I like here is that alpha 1 is the place where I see string perturbation, so I like the alpha 1 root. And 3 alpha is the same in every dimension. It's the same in 10. It's dimension independent. And the same for this one. You see the same 5 valves that you know in 10 dimension if you choose the alpha 1 here. It's amazing, but it's a very, very, very beautiful way to tell you what are these couplings. Okay, and I show that there's some universality there. Okay. So now I can do what I did here, except that instead of computing the constant term, I can look at the Fourier mode. So the Fourier mode of a generic series, they are, let me see, they are given by so what I have to do is that when I compute a Fourier mode, essentially I want to see if I call theta the phases that are in this unipotent factor. A physicist would write, I would write, so exponential 2i pi. So if here the space of my theta is n dimensional, I would take a vector that I will call capital N, that is of n dimensional, n times theta, and then I would integrate my series dpq phi respect to this phase, okay? So that means this is computing the Fourier mode respect to my parabolic subgroup, okay? So if I am looking at the alpha 1 parabolic subgroup, this is looking at the phase with respect to the de Bruijn charges that wrap my torus, so I will look at the instantaneous sector with respect to string perturbation. If I look at the last node parabolic, I will look at the instanton that come by wrapping BPS states in higher dimension on a circle, okay? So black hole states that contribute to my amplitude. But here I have to be a little precise because, I can really do it if this is abelian, okay? So essentially, in most of the case, this is abelian. Sometimes it's non-abelian. So when it's non-abelian, I take the commutator and I just compute it on the, on the abelian part. So I just. Okay. So now, what's happening is that I get an object that I'm calling f. It depends on n, so the set of integers here. And it depends on little phi. Well, of course, it depends on p and q. Okay, so my notations are not so good. Okay, let me put n here and phi, where phi are in the part of the duality group that is left when I've taken the parabolic. So, for example, if I do the string perturbation in the SODD divided by SOD cross SOD, if this is the last node, the decompactification in it, it's ED divided by its maximal parabolic subgroup. So Okay, so there is the element M alpha that is in the levy. Okay, so now this Fourier mode turns to have a very interesting properties, and that I can list. That are the following. So, first one. Okay, so there is one thing that one has to understand, is that if I act, for example, let me take the Fourier mode respect to the last node. So this is, for example, let me take, for example, E7. I'm looking at now P alpha 7, where the Levy factor is GL1 times E6. Okay, so this is the circle of compactification. So my phi are E6 modulus. So if I act with E6, so if I act with a transformation that is in, for example, E6 divided by I forgot what is the maximal USP whatever. Oh no, if I act with transformation that is in E6Z on the phi here, my Fourier mode, are not going to be invariant because I will have to have a compensating transformation on the integers. So I will transfer the action from one to the other, and the full function is invariant. Okay, but there is a natural action on the levy on okay, when actually the group here is non-abelian. Okay, so if I act on phi, that means I have to act on n a compensating way. But if I act on n, I have to act on theta as well. Okay, so there is you understand that in order the series to be invariant under your duality group, you have to have an action of E6 on all the phases that are here. So they are all the charges of your instantons that you get that contribute to your specific coupling. Okay, so there is a natural action on the thetas that are in the unipotent factor. What I'm saying is true for any parabolics. And these guys actually, the action is the natural action you expect, because for E7, what you have is that you have E6, and the thetas here, the thetas, they are in the 56, no, the 27, sorry, of E6. So if you take E7, E8, and you look at the decompactification from 3 to 4 dimension, the duality group that you are left, as explicit is E7, then the theta, the phases, they are in the 56 of E7, 56 representation of E7, but in that case, there is, a non-commutativity, there is as well a scalar. But when you look at E7, coupling in 4 dimension, and you look at the instantons, so they would come, for example, from instantons that you have. So in that limit, when you decompactify, you would see black hole states that you are wrapping on the circle. They are the thetas here. They give you the state, the E6. The black hole that have a charge in the 27 of E6. Okay. And so in general, E6, when you decompactify, you have SO55, and the thetas are in the 16 representation of SO55, the spinor. If you have E5, which is SO55, then you have SL5, and the angles are in the antisymmetric representation of SL5 of dimension 10. Okay, so there is a natural linear action there. And what's going to happen is that actually for this the action of the group, actually this action is going to give you orbits in this space of phases. So the action of the group, the action of the duality group, they give you orbits in the theta space, in the charge space. the theta space. Okay. So here I'm talking about continuous orbit, although clearly by the Fourier transform I'm transferring the continuous orbit to discrete orbits. But okay, this is okay. Now the statement is the following: is that so since this is a big statement, and I want to write it. So far, I mean, what I said is very generic, and I didn't use anything that is special to the series that we are looking at. But then there is a theorem, I mean, in mathematical sense, which is that for the series E00, which is E alpha 1 3 halves, okay, the non-vanishing Fourier mode, are for, okay, so theta in, so if I take the Fourier mode respect to the last parabolic in the half BPS orbit under the action of the duality group. So in particular, if I look at this, the Fourier mode respect to the last parabolic, which corresponds to the case I wrote it, that means the thetas here, they have to lie in, for example, if I take E7, they will have to be in the orbit that is the half BPS orbit, which is E6 with stabilizer that is SO55 times R16. So in a sense, now what we see when we look at the R to the fourth coupling, when we compute the Fourier mode, if I take a generic configuration of the thetas, then the Fourier mode will vanish. And then I can ask what is the minimal set of the thetas such that the Fourier mode are not vanishing. So in a sense, I want to determine what is called the wavefront set. So this minimal set is actually supported on a very specific orbit. So in each of the parabolic, actually I can do it, which is actually the minimal orbit. What people in mathematics call minimal orbit, but that turns to be when you work out what are the conditions. I mean, you can do it. I mean, I gave you a definition in terms of the Langlands Eisenstein series. You can compute the Fourier mode. You can see what are the conditions on the thetas so that the Fourier mode are non-vanishing, and then you will get a matrix condition that you realize is the one that has been listed by Ferrara and Maldacena as the 1 BPS condition. And you can do it in the other parabolics as well. So now we have a statement that is both mathematical and physical statement, is that this series has only non-vanishing Fourier coefficient on the smallest, actually in that case it's character variety orbit. That means orbit when I'm looking at the group that is in the levy, or if I don't want to make a reference to a levy, to a parabolic, is the smallest nilpotent orbit in terms of coadjuvant nilpotent orbit. Now, if I look at the next coupling, which is the d to the fourth r to the fourth, which is the 5 halves, then I see that the non-vanishing Fourier mode occur for one, the smallest nilpotent orbit, which is the half BPS state, and the next to what we call the quarter BPS orbit, which is the next to minimal orbit. Okay. So there is a piece of mathematics that I didn't have time to explain, and I'm going to violate my unitarity bond, is that the nilpotent orbit, they satisfy a natural order respect to inclusion, to closure. So, okay. So there is the trivial orbit, there is the minimal orbit, to the coadjuvant action, and then there is a next to minimal orbit, next to minimal. And then here there is some fuzzy structure, I mean it's very complicated. And then here there is the regular orbit that is the full group, and then there's subregular. Okay. And so this is included. So there's an this one is included. No, okay, I'm sorry. This one is included in this one. Okay. So what I'm saying is that so the support of the wavefront associated with an automorphic form is the largest nilpotent orbit for which the Fourier modes are non-vanishing. So for the R to the fourth term, which is the free life, I see that this is the minimal orbit. And I repeat, I mean, if you don't know what is a minimal orbit, you take the function, you work out what are the conditions on the theta, and you find on the nose the BPS condition, BPS condition. And here you do it, then of course you find that there are two types of contribution, 1/2 and 1/4, and that's it. I mean, everything that is bigger makes a vanishing Fourier coefficient. I mean, if I had more time, I would show you some explicit examples. So in a sense, what you can tell is that this free half phasation size that is R to the fourth is an automorphic representation of the minimal representation, and the D to the fourth R to the fourth, S equal 5 halves, is an automorphic representation of the next to minimal representation. Okay.
What do
there are various
lines? What do the lines mean in that diagram?
Oh, it's
The closure of one orbit.
yes. The point is that
The boundary one is the.
I mean, what happens is that the orbits, it's a very complicated thing. Is that yes, you branch. I mean, so you can go when you look at the structure of the nilpotent orbit. When you look at the way they are embedded in another nilpotent orbit. Yeah, after the next to minimal, you can go to another branch. Okay, so for example, there can be. Well, maybe I have the drawing here for E7, which I took from the Atlas group. Okay, I don't know. I mean, I don't know. So, for example, I will have an orbit that I call O1 here, O2 here.
And these are like branches, and the.
Yeah, branches. Yes, yes. So, for example, the 1/8 BPS orbit is one of the two branches. For example, here. So you can see that actually, when you look at E7, I mean, you want that, okay, the 1/8 BPS orbit that gives you BPS black holes, I mean, goes on one direction. And the other one, they are not associated to what you call BPS states. But, I mean, it's very confusing. I have no real understanding of what's going on. But here things are simple. So what I want to say is that the case S equal 3/2 was already studied by Kashdan and Ginzburg, Alice, and Soudry in mathematics, where they showed that actually the relation, I mean, the fact that what I said about the Fourier mode for from various cases, and that you can, I mean, there is an abstract proof of the relation between the minimal orbit and this specific residue of an Eisenstein series. For the S equal 5/2 case, it's new. I mean, in sense, I mean, it was not known before. So.
Do you expect the other orbits to appear in supergravity actually as well?
I don't know. I mean, it's I mean, as I said, I mean, I don't have a very good understanding about the structure of the orbit. I know Guillaume Bossard has, I mean, certainly, I mean, explained, I mean, how all this orbit can appear in supergravity solution, and definitively, if you want, for example, to take a point of view of, okay, the Fourier modes are related to instantaneous correction. So you can think, okay, I want to do a field theory, quantum field theory computation in the background of an instantaneous. So certainly, what Guillaume did about the analysis of the orbit that I have not discussed here will certainly be important. But I mean, I don't want to say anything because I don't understand it. But I'm sure this is important. Okay, so my time is up, I suppose.
Any questions?
Yes.
I think you wrote something down like this E alpha 1 3/2 and the other with 5/2 is only valid for certain dimensions. What happens with the others?
Okay, thank you for asking the question so that I can use more time. Well, I mean, I mean, it's a few more lines. It's just because lack of time, I was a bit lazy. So, so for that to the fourth term, it's okay. I can write it from top of my head, but so it's E D alpha 1 3 half up to just let me show. So up to D equal 7. So for D equal 8, the group is SL3 cross SL2. Okay, so I mean something special happens here, and there is a lot of interesting things. So here, actually, I mean, so it's E SL3 alpha 1 3 half plus 2 SL2 alpha 1 equal 1. But if I write that, it's not quite right, because, okay, if you see in D equal 8, the eigenvalue is vanishing. So here I'm sitting on the pole of the SL2 series, I'm sitting on the pole of the SL3 series. Okay. So actually, the solution is limit epsilon going to 0 of this. And amazingly enough, I mean, and there is some, amazingly that function is analytic. So as a function of S, if you, I mean, so as a function of epsilon, this is an analytic function. There is no pole for that linear combination. So string theory, you know, string theory has no divergences, okay? It has to be finite. And in D equal 9, this is, so the group is SL2 times R. So this is mu to the minus 3, 7, ESL2 3 half plus mu to the 7 fourth, and there is a 4 zeta 2 here. And in 10 dimensions, this is back the SL2 at 3 half. Okay. And for the D to the fourth, I just want to write an example, which is so in D equal 4, 4, 5, 6. In 6 dimensions, then the duality group is so 5, 5, it's E5. Yes, I just write one formula. And then what happens is that this is the SO55 series at alpha 1, 5 halves, as before. And then there is an SO series at 5 halves, but then it's for a spinor node, so 5 at 3. And again, for this series, you sit on the pole. So plus epsilon, limit epsilon going to 0. It's finite. So in a sense, I mean, there's nothing very wrong. In a sense, I mean, I'm taking a big object, which is the Eisenstein series defined by Langland. I'm taking a residue. And if I compute my residue in a stupid way, I can have one function that has a pole, another function that has another pole, and the residue cancel. So here, this is just a stupid way to write it. So for the SL2 series, the residue of the pole is a constant. Okay? Here, the residue of the pole is an automorphic form, so you have to work a little more. But, you know, string theory is finite. And I hope everybody agrees with that, so it has to work. So I'm going to stop because I've discovered supersymmetry.
Very good. Well, perhaps we should end here, and then people can ask questions to you directly. You're here how long?
Until the middle of next week.
Middle of next week.
Yes.
Okay, thanks.